Now, the algorithms we were studying follow some steps, and these steps, the number of times that you repeat these steps, determines how efficient the algorithm is. Now, we're not going to go into deep detail about the growth of functions and the complexity of algorithms, because that's a subject that you will study in other courses. But for now, we'll touch on a number of concepts, including first the big O notation. So the big O notation is a notation that helps us compare apples with apples, pairs with pairs, so that you can compare two different algorithms and tell which one is more efficient. So if we go back to algorithm 1, remember that was the linear search algorithm, where you were looking for the maximum. Sorry, you're looking for the maximum element in a finite sequence. So if you consider this algorithm, you say that if you want to assign a maximum number of steps that this algorithm will perform, there is a notation for that. Since the number of instructions that you will perform is asymptotically the same as the input size, then we say that the algorithm is big O of n. So that means when I say asymptotically, and that's a word that, again, you will study in another course, but for now, I will tell you that this means that if you were to increase the input size significantly, that means asymptotically you have to perform a number of operations which is similar to the input size. So there is a number of big O standard benchmarks that have been established so that you can compare algorithms in an easier way. And we have this notation. Now, we're not going to prove that which of these applies to what algorithm, but the objective here is that you are aware of this big O notation and that you know the meaning of it. So if you say big O of 1, that means that the number of operations that an algorithm has to perform is not dependent on the input size. So it will always execute a fixed amount of instructions to achieve its goal. On the second one, you have the big O notation for log of n. So log of n means that the input size is n. So to perform its task, the algorithm will go through log of n instructions. We just talked about the big O of n. Then we also have the n log n squared, 2 to the power n, and n factorial. So these benchmarks are in order of efficiency. So the first one is the most efficient. The last one, n factorial, is the least efficient. So when you see two algorithms that are meant to perform the same task, but they have different big O complexity, then you know which one is best. But how do you come up with this assignment for big O notation? Well, when you analyze an algorithm and then you say, yeah, this algorithm is going to perform x to the power 3 instructions. Okay, x could be, I don't know, 3 to the power 3 instructions. Then you know the algorithm is x to the power n. So when you come up with a complex expression that describes the number of instructions that the algorithms need to perform, you can just go at the one with the highest exponent, right? And then use that as for the complexity of n. In this case, a is a coefficient, x is a variable, n is the input size. So you can ignore the coefficient here. You just write the variable and the exponent, and the exponent is in terms of the input size.